Good morning, everyone. Thank you for being here. Today with Charlie, we will talk about smart subsampling for predictive modeling and how this approach has evolved over the last decade through applications in material science. This work is the result of a long and strong collaboration between Scie and Ipon Innovation. And this is how this work was motivated. We often hear that data size is no longer a problem because modern machine learning algorithms can process massive data sets. But in practice, what we see is that handling large data sets still presents real challenges. Brute force approaches, meaning processing everything just because we can lead to inefficiencies, overfitting, and noise accumulation. So the key idea behind this work is that using all the data is not always the smartest strategy, and an alternative is intelligent subsampling by selecting a representative fraction of the data instead of using everything blindly. Beyond computational efficiency, subsampling also encourages more interpretable models because reducing data set size often makes relationships between variables clearer. So the question is, how do we subsample intelligently without losing predictive performance? The present subsampling approach is not new. We presented it first at Discovery Summit Europe in 2020, and since then it has been improved a lot. Over the years, several methodological improvements have been introduced, significantly enhancing its predictive performance. And we will show during this presentation that today the approach is robust enough to compete with classical machine learning algorithms and in some cases even outperform them. Here are just a few words about CEA. The CEA is a French government research organization involved in low carbon energy, digital technologies, health technologies, and defense. I won't go through all the numbers in detail, but the key message here is the scale of CEA with more than 20,000 employees, multiple research centers, and a strong focus on innovation.
Hello, my name is Charlie Marty, and I worked as a data scientist in Ipon Innovation. Ipon is a company of data experts dedicated to provide industry with advanced algorithms. So our objectives are to optimize manufacturing costs and test times for our customers, to improve the quality of complex products, to detect small signals in big data. We propose services of consulting, training, and on-demand advanced studies. We have several products such as customized statistical solutions or advanced tools, with some of them that are patented. And as a JMP partner, Ipon also trains users in JMP.
Okay, when we speak about data, the message here is that smarter doesn't always mean bigger. And this message really summarizes the philosophy of the work, because the goal is not necessarily to use more data, but to use the right data. And a key observation behind this work is that real databases are rarely uniform. Some regions of the experimental space are very densely populated, while other regions contain only a few points. Some data may come from isolated studies, design of experiments, or one component at a time experimentations. And when we apply brute force modeling, all these regions are treated equally, even though they do not carry the same amount of information. So the core idea is, instead of trying to model everything at once, we focused on what really matters locally. For a given target point, not all data points in the database are equally informative. Some points are very relevant, some points are much less informative. So the basic idea is therefore quite simple: predict locally by training models only on data that are similar to the target point. In other words, instead of building a single global model, we dynamically construct a local training database for each prediction. And this is the major advantage of the method. Rather than randomly splitting the database into training, validation, and test sets, we maximize the use of similar data for each prediction. The training data are not selected randomly, but based on their relevance to the target composition. And the good news is that this approach can be implemented directly in JMP, as we will see with a bit of GSL. And everything we will show today, from subsampling to modeling, is fully automated. Let me give you a bit more context on the application case. Glass is a non-crystalline solid obtained by melting and cooling a mixture of oxide precursors such as silica, alumina, and many others. And depending on the application, glass compositions can range from very simple systems with just a few oxides to highly complex formulations with dozens of components. Glass viscosity is particularly challenging to model, because from strain point up to the melting temperature, viscosity spans more than 13 orders of magnitude. This makes accuracy prediction difficult across wide ranges of temperature and composition. And on top of that, glass viscosity is extremely sensitive to composition. Small changes in oxide content can trigger phenomena such as fast separation or crystallization, which may lead to abrupt viscosity changes. These effects often occur within very narrow regions of the composition space, making global prediction modeling approaches particularly difficult. So, because glass viscosity combines high dimensionality, strong nonlinearity, and highly uneven data distributions, we strongly believe that this is an excellent application case to evaluate the smart subsampling approach. At this point, the key methodological questions become very concrete. First, which data should we consider similar enough to build an optimal training subset? Second, how far should similarity be extended around the target point? And finally, how do we define similarity in a high-dimensional composition space? The first step is to build a virtual optimal mixture design around the target composition. This DOE is theoretical. It defines where we would ideally like to have experimental points given the prediction problem we want to solve. At this step, expert knowledge really plays a key role in terms of boundaries definition, constraints, and feasibility rules to ensure that the design remains physically and chemically meaningful. And this is where the expert knowledge is explicitly integrated into the workflow. Instead of letting the algorithm explore unrealistic regions, it is possible to guide it using non-composition limits and formulation rules. At the end, this makes the modeling both more robust and more interpretable. In the second step, we replace the theoretical DOE points with real experimental data coming from the database. Each virtual DOE run, for each virtual DOE run, we search for the most similar experimental compositions available and use them to build the final training dataset. The result is a compact and targeted training dataset that is specifically tailored to the prediction of interest. And instead of thousands of points, we typically end up with a limited number of highly relevant observations. Of course, everything depends on how similarity is quantified. We explored several distance metrics in composition space: Euclidean distance, which is just a particular case of Minkowski distance matrix, was evaluated, as well as several values of the Minkowski P parameter. And interestingly, the best predictive performance was obtained for a parameter value of 0.5, which emphasizes local similarity even more strongly than the Euclidean distance. Weighting the distance metric, where each compound contributes with its own weight, also proved to be an effective way to further improve performance. Once the final training dataset has been constructed, we move to the modeling step. We wanted to implement several types of predictive algorithms, ranging from classical statistical models to more machine learning-like algorithms. This allows to evaluate whether the subsampling strategy is robust across very different modeling approaches. Specifically, we implemented 4 algorithms: a polynomial mixture model, which is very popular in mixture DOE, a generalized linear model, which handles strongly non-normal data more robustly, neural networks to capture complex nonlinear relationships, and support vector regression, which is generally less sensitive to outliers. The idea is not to pick a single best model, but to exploit their complementarity. And one interesting outcome of the approach is the size of the final training datasets. For simple class compositions, we typically use around 40 points. And for more complex compositions, this increased to about 100 points. But despite these relatively small sample sizes, predictive performance remains very strong, as we will see just after. This schematic summarizes the full workflow, starting from the input. The tool generates a virtual DOE, selects similar experimental data, and then runs multiple predictive models. From the user perspective, all of this is handled automatically. The tool produces a wide range of outputs. These include predictions from the different models, but also classical goodness of fit indicators, prediction variance, and diagnostic plots. The goal is not just to provide a number, but to give users enough information to evaluate the reliability of the prediction. As we said, all steps of the workflow are fully automated and implemented in GSL. The tool is now an add-in compatible with JMP 19 and earlier versions. To evaluate the capability of the tool, we tested it on 4 large datasets with a total of more than 21,000 data points. Computation time remains reasonable, less than 1 minute for single prediction and a few days for large batch predictions, which is for us fully compatible with real-life utilization. Okay, now let's move on to the demo with Charlie.
Okay, so the MS-ProV tool has been developed as a JMP add-in, and it provides 2 different ways to predict glass viscosity. So the first one corresponds to the standard user workflow. It allows the prediction of one or a few glasses at one or several temperatures, with a graphical output that helps analyze the results. The second option here runs predictions on our entire database of more than 7,000 glasses. This mode is mainly used to evaluate and compare model performance. So when using the add-in, the user must first enter the chemical composition of the glass to be predicted. Several input methods are available. The first option is to select the element from this list, then click on OK here, and another tab let the user enter the corresponding composition percentage for each element. The second option is to copy and paste a composition from an external file. And the last option allows the users to predict multiple glasses at once. This is done using this template file here, where the user can add one glass composition by row. So when the jump table is complete, the user can upload it into the add-in via this button. Then the user have to define the prediction parameters, in particular the temperature at which viscosity should be predicted. So for instance, from 1200 to 1300 with a 50 degrees step, and then select the prediction method to be used. So in our case, it will be a DO-based methods. So once the prediction are launched, this main script is executed. The scripts define the overall structure and codes several other scripts in order to apply the parameters defined by the user. So for instance, this jump expression will predict viscosity with DOE-based methods. So the add-ins contains more than 30 scripts, as we can see here. Some are dedicated to the graphical interface you just seen, and others are implementing the prediction models themselves. We can also find an XJBoost folder inside the add-in. This is actually another add-in dedicated to XJBoost-based predictions. It is embedded directly into MS Pro V so that the user does not have to manage the installation or maintenance of XJBoost. So once the predictions are completed, a graphical output is presented to the user. So first, there is a reminder of the glass composition for which the viscosity has been predicted. So we have each chemical element with the corresponding percentage. Then the elements included in both the theoretical and adaptive DOE are displayed. We also provide some quality metrics for all the models, such as mean absolute error here and the R-squared. The model details section contains data tables, including the one used to train the models. It also includes a scatter plot matrix here. This matrix shows the distribution of the theoretical DOE points in blue here, the glasses used in the adaptive DOE for model training in red here, and the composition of the glass of interest in green. So in this example, the compositions of the training glasses cover the theoretical DOE. As we can see, the red adaptive DOE points are located around the optimal DOE points in blue, which are themselves around the composition of the glass of interest. So next, we display prediction formulas for each model, as well as the parameter with significant impact on viscosity here for the big forward method. So then we have the main graph here. This is the most important output for the user. It shows the predicted viscosity values for each model. So in this example, JLM here in red and big forward method in blue are very close, around 169. And the neural network predicts a higher value close to 200. And SVR predicts a lower viscosity value here. The median of those predictions is also shown, as it has interesting robustness properties. This graph also includes this green dashed line, which represents the measured viscosity of the nearest glass. And at the bottom of the page, all the associated information for this glass, such as its origin, the year it has been measured, its composition here, and the distance with the original glasses, as well as the predictions of our models. And finally, the user can access to this results table. So this table presents the composition of the glass of interest here, the composition of the neighbor glass. It also shows the model predictions, their median, and additional data, such as the distance between the two glasses and some measure of the quality of prediction. A similar table is also generated when running the automatic prediction on the full database of 7,000 glasses. This enables a more in-depth analysis, which Damien is going to present now.
Okay, so let's now look at the predictive performance. As we said just before, we evaluated prediction accuracy on 4 datasets for a total of about 21,000 data points. The metric we focus on is the median absolute error to quantify the deviation between predicted and reported viscosity in orders of magnitude. In glass material science, achieving accuracy with 1 order of magnitude is generally considered highly effective. This slide shows the distribution of the absolute errors with color points indicated in the reported versus predicted graph. The data points are tightly clustered around the diagonal, which indicates good agreement over the entire range of viscosities. And this is really encouraging given the extreme dynamic range of the property. The median error is very small, around 0.07 in log scale, which corresponds to roughly 15% relative error. And what is particularly remarkable here is the behavior of the error quantiles. The vast majority of the predictions are well within 1 order of magnitude, and the upper quantiles of bad predictions remain very low. So this shows that the approach is not only accurate on average, but also very robust with excellent performance across the full distribution. When we look at the individual algorithms, we see that they all deliver comparable performance. Neural networks and support vector regression are slightly less sensitive to outliers, as expected. And what is interesting is that taking the median of the 4 predictions is slightly better than each individual model. A natural question is how this approach compares with k-nearest neighbors, because KNN is also a local method which predicts the response value by using the average of the responses in the neighborhood of the target. And we see that our approach clearly outperforms KNN, showing the importance of combining a smart and local data selection with proper modeling algorithms rather than relying on distance-based averaging alone. Finally, we have benchmarked our approach with brute force modeling by using 2 state-of-the-art machine learning techniques, boosted trees and XGBoost. So first, when the goal is to obtain accurate predictions across the full dataset domain, performance is comparable, very close to XGBoost, and slightly better than boosted tree, which is already great news for us to reach best up-to-date brute force machine learning algorithm. But the real strength of the approach becomes evident when focusing on targeted domains in the smaller regions of interest where local accuracy really matters, Smart subsampling consistently delivers significantly better precisions than brute force approaches. To conclude, we proposed a smart subsampling methodology as an alternative to brute force approaches. Instead of randomly partitioning large datasets, the method focuses on selecting the most relevant data for the prediction. The entire workflow is fully automated, implemented in JSL, and available as a JMP Pro add-in. Overall predictive performance is comparable to state-of-the-art machine learning techniques, but on targeted regions of interest, where locally accuracy really matters, smart subsampling delivers significantly better predictions than brute force approaches, while offering better interpretability and easier integration of expert knowledge. So that's why we believe smart subsampling represents a promising approach for a wide range of applications, well beyond material science. And one last thing before we finish, this approach was first presented at Discovery Summit Europe in 2020. And after several years of development and validation, maybe it's time for the next step. Thank you very much.